In this video, we're going to take a brief look at the SN1, SN2, E1, and E2 mechanisms. You finally made it to the fun of organic chemistry. Most people get really freaked out at the onset, but I personally found organic to be a lot more fun and comprehensible than all the computational work in general chemistry. So I'm going to first start out with a few conceptual things that I think are important to know before you start getting to the actual arrow pushing mechanisms, with the first thing being this lovely chart I've compiled for you here. Given the level of the substrate and the strength or weakness of the nucleophile given to you, you can determine whether the reaction will proceed through any of these four mechanisms. Below this, I've included the most common strong and weak nucleophiles and bases that you will see moving forward. This is definitely not a comprehensive list, but you will certainly see these compounds a lot throughout the course, and it's important for you to understand their role early on, so that later, as you get into the more complex mechanisms, your brain will have a general understanding of their properties. I would highly recommend committing everything on this slide to memory, including these protic and aprotic solvents. Protic solvents, if you didn't already know, are those that are capable of hydrogen bonding. And depending on whether you're working in terms of an SN2, SN1, E2, or E1 reaction, a protic or an aprotic solvent may be favored. In an SN2 or E2 reaction, aprotic solvents are ideal, whereas in an SN1 and E1 reaction, protic solvents are best. I will go into more detail on this as I begin discussing the basic concepts involved in each of these four pathways. So the first pathway we're going to start with is the SN2 bimolecular substitution reaction. The SN2 reaction is bimolecular because its rate depends on the concentration of both the substrate and the nucleophile. The SN2 mechanism is concerted, meaning that both steps, the nucleophilic attack and the loss of leaving group, occur simultaneously. SN2 reactions occur fastest in aprotic solvent, like I said before, but I didn't explain why. So if you had a protic solvent, the one that is capable of hydrogen bonding, it would solvate the nucleophile, making it more difficult for the nucleophile itself to access the electrophilic site, and it would thereby decrease the reaction rate. So let's say we start with this compound, 2-bromobutane, and we react it with sodium methanethiolate and DMF, a common aprotic solvent. Our substrate, the 2-bromobutane, is a secondary substrate because the alpha carbon attached to the halide is attached to two other beta carbons. Sodium methanethiolate, if we look at our chart, we can see is a weak base and strong nucleophile. So therefore, we know this has to proceed through an SN2 reaction based on the chart. The presence of that aprotic solvent is also another big hint toward the appropriate pathway by which to proceed. As mentioned previously, this is a concerted mechanism, so the nucleophile, the methanethiolate, will attack the alpha carbon and kick off the bromine. Bromine is a good leaving group. And if you didn't know, a good leaving group is defined as a weak base or the conjugate base of a strong acid. So the order of the best leaving groups, starting from best to worst, would be iodide, bromide, chloride, and then fluoride. SN2 reaction proceeds with a backside attack, so the major product will always include the substitution product with inverted stereochemistry. If we start with a substrate with the substituent on wedge, our product will always be on dash and vice versa. You will not get a racemic mixture in this case, so just remember for SN2 to always invert the stereochemistry of your product. The second pathway we're going to study is the E2 or bimolecular elimination reaction. Again, this is bimolecular because the rate depends on the concentration of both the substrate and the nucleophile. This is another concerted mechanism, so everything will happen in the same step. Let's say we start with this compound, 1-bromo, 2-ethyl, 1,5-dimethyl cyclohexane, and we react it with sodium ethoxide. Sodium ethoxide is a strong base and strong nucleophile, and because our substrate is tertiary, this will definitely proceed through the E2 mechanism. The ethoxide will serve as a base, extract a beta hydrogen, and kick off the leaving group, forming an alkene. The product we will get from extracting this hydrogen in particular will be the major product. However, there are two other possibilities to consider. we can remove this hydrogen, or we can extract this hydrogen. Here are the major and minor products of this reaction. How did I know which beta hydrogen to extract to form the major product? Well, because we have a small base, the sodium ethoxide, I know our major product will contain the more substituted alkene. The major product in this case is tetrasubstituted, whereas the two minor products are trisubstituted and disubstituted. The most substituted alkene is known as the Zaitsev product, and you will know to form this product if and only if you have a small base. Let's look at a case in which we will form the less substituted alkene as the major product. So here we have 1-chloro-1,2,4,4-tetramethylcyclohexane, and we're going to react it with a bulky base known as tert butoxide. This is the most common bulky base you will see, and during my time in this course, this was the only bulky base I ever saw. So for now, just know that if you see this, you are working with a bulky base, and because it's a bulky base, we will form what is known as the Hofmann product, or the less substituted alkene. The more substituted alkenes will be the minor products. And the idea here is that the bulky base will react more rapidly with the least sterically hindered proton on a beta carbon because the base is too big to readily extract a proton from a more sterically hindered position. Okay, now we're going to look at the SN1 and E1, or solvolysis pathway. If we look back at our chart, we see that the only case in which we will proceed with this mechanism is when we have a tertiary substrate and react it with a weak base and weak nucleophile. This can be water, methanol, ethanol, any of those. But one of the most significant differences between the SN1 and E1 when compared to the SN2 and E2 reactions is that in solvolysis, the rate determining step is the formation of the carbocation. We will therefore not continue in terms of a concerted mechanism, and instead will first kick off the leaving group and form a positively charged carbon center. Once this carbocation has been formed, we will perform both a substitution and an elimination reaction and form their respective products in relatively equal quantities. For the SN1, the water molecule will serve as a weak nucleophile and attack the carbocation. In the next step, because we have plenty of water in solution, the water molecule will also serve as a weak base and do a proton transfer to neutralize our final product. For the E1 reaction, the water molecule will serve as a small weak base, extract a beta hydrogen at the more substituted position, and form an alkene. Both of these products here are considered major products. So if asked to predict the major product, both structures should be included in your answer. Here are some practice problems for you to check your understanding of what we've gone through up to this point. I encourage you to pause the video now, work these out, and then check your answers. Okay, here are the products of each of these reactions and the mechanism under which each of the products were formed. Before I end this video though, I want to encourage each of you to practice relentlessly. It has now been a year since I took my first semester of organic chemistry, and because I spent so much time working out multiple practice problems for each mechanism, working out these problems now has become a thing of muscle memory. The more you understand the foundations of the course as you begin, the better you will do later on. Another thing I want to mention is it's better to fail in the beginning than later on in the course. Don't get discouraged if you struggle with this in the beginning. It's like learning an entirely different language, but if you're persistent enough, you will overcome this learning curve and sail through the class. There is no getting around the hard work, but I think most students come into this class with the idea that it's going to break them and then possibly weed them out of their biomed major. Again, I find the conceptual nature of this course to be much easier than what I saw in Gen Chem, but if you find yourself stumped and in need of more help, feel free to comment below and I'd be happy to get back with you with an explanation. That's all for now. I'm looking forward to hearing from you.